Hello there. Let your body settle. Let every muscle that has been holding you upright through the day finally release its duty. You don't need to hold anything together right now. The universe is doing that for you. Tonight, we are going to space. Not urgently, not in the way of alarms and countdowns and blazing engines. We are going slowly, the way you drift into a dream, with curiosity, with calm, with the particular kind of wonder that blooms only in the quiet hours. Tonight we will explore 100 of the most relaxing, most quietly extraordinary facts about the human journey beyond Earth. The physics that lifts us from the ground, the silence of the vacuum between worlds, the strange and beautiful science of living in weightlessness, the engineering of spacesuits and rockets and generation ships, the psychology of floating in the dark, alone and small, with the whole of human civilization reduced to a pale blue point below. There is no rush. There is no urgency. Space is extraordinarily patient. It has been waiting since before the first human looked up and wondered. And it will continue waiting long after all our questions are answered or forgotten. You are here. The stars are there. The distance between is full of wonders worth resting inside. Let's begin. Every object leaving Earth must overcome something called escape velocity, the minimum speed at which a body can travel upward from the surface and never return, assuming no further propulsion after the initial push. For Earth, that speed is approximately 11.2 kilometers per second, or just over 40,000 kilometers per hour. This is not a number chosen by engineers. It is a consequence of Earth's mass and radius, derived directly from the equations of gravitational physics. Anything traveling slower than this, thrown upward without continued thrust, will eventually be pulled back. Anything reaching or exceeding this speed, if pointed away from Earth, will continue outward indefinitely, slowing as it climbs against gravity, but never quite stopping. The concept sounds simple, stated plainly, but to actually accelerate a mass to that speed against the resistance of an atmosphere and the constant downward pull of a 6 septillion kilogram planet requires everything we have learned about engineering, chemistry, and physics, the foundation of all rocket science, the equation that governs how much propellant a rocket needs to achieve a given change in velocity, was derived not by an engineer working on a launch pad, but by a Russian schoolteacher named Konstantin Tsiolkovsky, but by a Russian schoolteacher named Konstantin Tsiolkovsky, but by a Russian schoolteacher named Konstantin Tsiolkovsky, named Konstantin Tsiolkovsky, but by a Russian schoolteacher named Konstantin Tsiolkovsky, named Konstantin working in intellectual isolation in the late 19th century. His rocket equation, published in 1903, relates 3 quantities: the exhaust velocity of the propellant, the ratio of a rocket's initial mass, fully fueled, to its final mass after burning fuel, and the resulting change in velocity the rocket achieves. The elegance of the equation is also its cruelty, because velocity change depends on the logarithm of the mass ratio. The amount of propellant needed grows exponentially with the desired speed. To go twice as fast, you need far more than twice the fuel. To go 10 times as fast requires a mass ratio that borders on the physically absurd. Every rocket ever launched has been a negotiation with this fundamental constraint. A rocket moves not because its exhaust pushes against the ground or the air or anything external at all, but because of Newton's third law, operating in the pure and unambiguous form that the vacuum of space allows. When propellant is expelled backward at high velocity, the rocket body is pushed forward at a rate determined by the mass and speed of the exhaust. The surrounding medium, atmosphere, vacuum, it makes no difference, plays no role in this exchange. The rocket carries both its fuel and its oxidizer, which is why it can operate in space where there is no oxygen to support combustion. The act of expelling mass backward is the act of gaining momentum forward, and the physics of that exchange is absolute, invariant, and beautifully clean. Many people intuitively feel that a rocket must be pushing against something. It is not. It is simply throwing part of itself away, very quickly, in precisely the right direction. Modern orbital rockets are built in stages because of the tyranny of the Tsiolkovsky equation. A single-stage rocket attempting to reach orbit would need to carry so much propellant that the structural mass required to contain it would make the whole vehicle too heavy to lift efficiently. The solution, independently conceived by multiple engineers in the early 20th century, is staging building the rocket as a series of separate vehicles stacked on top of one another, each with its own engines and propellant tanks. The lowest stage burns first, accelerating the entire stack to an intermediate velocity, then detaches and falls away. The next stage ignites, now carrying only its own mass and whatever remains above it, and pushes the payload further. Each stage, abandoned, is dead weight removed, allowing the remaining stages to achieve far higher velocities than a single-stage design ever could. The Saturn V rocket that carried the Apollo missions to the Moon used 3 stages, each discarded in sequence, a Russian nesting doll of controlled explosions. Rocket propellants come in many forms, but the most efficient chemical propellant combination in routine use today is liquid hydrogen burned with liquid oxygen. The combination used in the upper stage of many heavy lift rockets. When hydrogen and oxygen combust, they produce water vapor as the exhaust product, expelled at extraordinarily high temperatures and velocities. The specific impulse, a measure of propellant efficiency analogous to the miles per gallon of a car, for this combination is among the highest achievable with chemical propellants. The difficulty is one of engineering rather than chemistry. Liquid hydrogen must be stored at temperatures near absolute zero, just a few degrees above the coldest possible temperature in the universe, making the propellant tanks cryogenic vessels requiring specialized insulation materials and handling procedures. Fueling a rocket with liquid hydrogen is a careful, deliberate process conducted in the hours before launch, a long, patient preparation for a very brief and very loud act of physics. The moment of liftoff, when a rocket's engines first ignite and the vehicle begins to rise from the launch pad, is governed by a simple condition. The thrust produced by the engines must exceed the total weight of the vehicle. Until that moment, no matter how hard the engines burn, the rocket does not move. Hold-down clamps keep it physically restrained on the pad, while the engines build to full thrust, ensuring that if an engine fails to reach the required performance, the vehicle can be safely shut down before it moves. When thrust exceeds weight and the clamps release, the rocket does not leap from the pad. It rises slowly, almost reluctantly, in a way that surprises first-time viewers. The vehicle is at its heaviest at this moment, full of dense propellant, and the initial acceleration is modest. But within seconds, as propellant burns away, the mass decreases, the engines maintain their thrust, and the acceleration increases until the vehicle is moving faster than any aircraft ever designed. As a rocket ascends through Earth's atmosphere, it passes through distinct regions of decreasing air density, each presenting different engineering challenges. In the dense, lower atmosphere, aerodynamic forces on the vehicle are significant. The rocket must be precisely pointed into its velocity vector to avoid destructive sideways stresses, and the nose cone must be robust enough to withstand the pressure of supersonic flight. The period of maximum aerodynamic pressure, called max Q, typically occurs roughly 1 minute after liftoff, when the increasing speed of the vehicle has not yet been offset by the decreasing density of the air. This is often the most structurally demanding moment of the ascent. Beyond max Q, the atmosphere thins rapidly. Aerodynamic forces diminish, and the vehicle's behavior becomes increasingly dominated by the clean, frictionless physics of space rather than the turbulent complexity of atmospheric flight. The boundary between those two worlds, though fuzzy, marks the beginning of something different. The Kármán line, the internationally recognized boundary of space, set at an altitude of 100 kilometers above sea level, is defined not by any abrupt physical change in the atmosphere, but by a practical consideration. At approximately this altitude, the atmosphere becomes too thin for a winged vehicle to generate meaningful aerodynamic lift, and a craft would need to move at orbital velocity simply to generate the lift required to stay aloft. Below this line, aeronautics applies. Above it, astronautics. The Kármán line is also approximately where the aurora borealis and the aurora australis form, where energetic particles from the solar wind collide with the upper atmosphere and produce those slow, silent curtains of pale green and crimson light. Crossing the Kármán line is the technical definition of becoming an astronaut. Under most international frameworks, it takes roughly 8 to 10 minutes aboard a rocket to cross it. The crossing itself feels to those who have experienced it like a door opening onto a room of extraordinary silence. Orbit is not what most people picture. It is not hovering in space, neutrally buoyant above the Earth. It is falling continuously, perpetually in a carefully arranged trajectory that curves away from the planet at exactly the rate the planet curves beneath it. An object in low Earth orbit, at an altitude of roughly 400 kilometers, is moving at approximately 7.8 kilometers per second, about 28,000 kilometers per hour, and it is falling toward the Earth at every instant. But because the Earth's surface curves away ahead of it at the same rate it is falling, the object never gets closer. It simply keeps falling around the planet, tracing an ellipse in the mathematics of gravity, perpetually descending without ever arriving. This means that astronauts aboard the International Space Station are not floating because there is no gravity. Earth's gravity at that altitude is only about 11% weaker than at the surface. They are floating because both they and the station are falling at exactly the same rate. Together, endlessly, the experience of entering orbit, as described by astronauts who have made the journey, involves a moment that is at once abrupt and deeply strange. The engines cut off. The roar and vibration of the ascent, which is the loudest and most physically intense experience many of them have ever had, stops completely in an instant. And in that silence, everything that was strapped down suddenly floats. A checklist drifts from a clip on the wall. Dust particles suspended in the cabin air circle slowly in no particular direction. The astronauts themselves, still strapped in their seats, feel the subtle pull of their harnesses as the only remaining directional force. There is no up, there is no down. The sensation is described variously as deeply peaceful, mildly disorienting, or both simultaneously. Most people adapt within a few hours, their vestibular systems recalibrating to a world in which the familiar equation of weight and ground no longer applies. Low Earth orbit. The region from roughly 200 to 2,000 kilometers altitude, where most crewed space activity takes place, is not a safe, static environment. It is filled with debris, defunct satellites, fragments from launch vehicle separations, remnants of anti-satellite missile tests, and the cascade products of previous collisions. The United States Space Surveillance Network tracks roughly 27,000 objects larger than a softball in this region, and estimates that there are hundreds of thousands of smaller, untrackable fragments moving at orbital velocities. A fragment the size of a marble, moving at 28,000 kilometers per hour relative to a spacecraft, carries the kinetic energy of a bowling ball dropped from a building. The International Space Station shields against small impacts with layers of Whipple shielding, a spacing technique that causes small projectiles to vaporize before reaching the inner pressure vessel, and occasionally maneuvers to avoid tracked debris. The vacuum of orbit is busy and crowded and requires constant attention. The delta V, the change in velocity, required to reach low Earth orbit from the surface is approximately 9.4 kilometers per second. This number, which appears in every preliminary discussion of space access, is not just a speed, it is a budget. Every mission is planned as a careful allocation of velocity changes. How much to reach orbit? How much to adjust the orbit shape? How much to rendezvous with another vehicle? How much to slow down and descend at the end? Each maneuver costs propellant, and propellant costs mass, and mass costs more propellant to lift. The interconnectedness of these costs, the tyranny of the rocket equation playing out in every mission plan, means that even small additional requirements cascade into much larger propellant mass fractions. Planning a mission to orbit and back involves a meticulous accounting of velocity, mass, and energy that leaves almost no room for the approximate. The physics is merciless and precise, and entirely without negotiation. The view of Earth from low orbit is something that no photograph truly reproduces, and no description quite captures. A fact repeated so consistently by the astronauts who have experienced it that it acquired its own name: the overview effect. The curvature of the Earth is apparent, but not dramatic at 400 kilometers altitude. The horizon is curved, the limb of the planet visible against the blackness of space, the atmosphere a thin and luminous blue arc clinging to the surface like a skin. Every 90 minutes, the sun rises or sets. In that 90-minute orbit, the crew of a spacecraft crosses oceans, continents, mountain ranges, and the dark terminator line, where day and night divide, watching weather systems that span thousands of kilometers resolve slowly below them. The Earth, seen from this angle, appears fragile in a way that it never does from within it. A world that fits within a window, small and bright and irreplaceable in all that surrounding dark. The International Space Station is the largest structure humanity has ever placed in orbit, a modular complex assembled piece by piece over more than a decade, comprising pressurized modules, solar array wings, truss segments, docking ports, and external experiment platforms. Its pressurized living and working volume is approximately 915 cubic meters, roughly the interior space of a 6-bedroom house. It orbits at an average altitude of about 400 kilometers, traveling at 7.66 kilometers per second, completing one full orbit of the Earth. every 92 minutes. The station is a joint project of 5 space agencies: NASA, Roscosmos, ESA, JAXA, and CSA, representing the United States, Russia, Europe, Japan, and Canada, and has hosted astronauts and cosmonauts from 19 different countries since its first crewed occupation. It is, by any reasonable accounting, the most complex and expensive object ever built by human beings, assembled in the most hostile environment our species has ever worked in, piece by careful piece, over more than a decade of spacewalks. Sleeping in microgravity is one of the more philosophically unusual experiences available to human beings. Without gravity, there is no preferred orientation, no sense that lying down is different from standing up, because neither position places any load on the body. Astronauts aboard the ISS sleep in small personal crew quarters, roughly the size of a phone booth, with a sleeping bag tethered to the wall to prevent them from drifting around the module while unconscious. The bag keeps them loosely in place. There is no mattress, no pillow, no sense of lying on anything. The arms tend to float upward during sleep in a position that looks, to outside observers, slightly ghostly, forearms rising above the torso with elbows bent, the muscles of the body offering no resistance because there is no gravity to resist. Sleep itself, once the body adapts, is reported to be quite restful. The absence of pressure points, of a body pressing its weight into a surface, is something many astronauts describe as unexpectedly pleasant. The ISS does not experience natural day and night on human timescales. The station orbits so quickly that the sun rises and sets 16 times in every 24-hour period. A sunrise every 92 minutes, each one lasting only a few minutes before the next sunset follows. To impose some biological order on this, the station operates on Greenwich Mean Time, and the crew's schedule is structured around a conventional 24-hour day, regardless of what the windows show. Artificial lighting within the station is managed to support the crew's circadian rhythms, gradually brightening in the morning and dimming in the evening, mimicking the quality and color of earthly daylight. The windows in the crew quarters can be shuttered to block the strobe of rapid sunrises during sleep periods. Without these measures, the human circadian system, evolved over millions of years to synchronize with a single 24-hour light cycle, would have no reliable cue to follow, and sleep quality and hormone regulation would suffer accordingly. Food aboard the International Space Station has improved considerably since the early days of crewed spaceflight, when astronauts squeezed purees from metal tubes and ate compressed food bars designed less for enjoyment than for caloric efficiency. Contemporary ISS meals are prepared on Earth, packaged carefully to prevent the release of crumbs, which in microgravity would float freely through the cabin, potentially being inhaled, fouling equipment, or contaminating experiments, and then rehydrated or heated on orbit. The menu includes hundreds of items: pasta dishes, soups, curried chicken, fruit cups, tortillas preferred over bread, which crumbles, pouches of coffee and tea, and even occasional fresh produce delivered by resupply missions. The loss of gravity alters the sense of taste somewhat. Fluid shifts in microgravity led to congestion-like states that subtly dull taste perception. So astronauts often find themselves preferring stronger, spicier flavors than they would on the ground. Exercise is not optional on the ISS. Without the constant low-level loading that gravity places on the human skeleton, the simple act of standing, walking, carrying one's own body weight through each day. The 59, walking, carrying one's own body weight through each day. the body begins to decondition at a rate that would render returning astronauts unable to stand or walk unassisted after a mission of only a few months. Bone density decreases at roughly 1 to 2% per month in microgravity. Muscle mass and cardiovascular fitness follow similar declining trajectories. To counter this, ISS crew members spend approximately 2 hours per day exercising using specialized equipment, a treadmill with a harness that loads the body against a bungee cord to simulate weight, a stationary cycle ergometer, and a resistance device called the Advanced Resistive Exercise Device that uses vacuum cylinders to simulate the loading effect of free weights. The exercise is effective, but never fully compensatory, and returning astronauts spend weeks in post-flight rehabilitation regardless. Water on the International Space Station is one of the most carefully managed resources aboard. The station does not receive unlimited water deliveries from Earth. Resupply missions are infrequent and cargo mass is expensive, so virtually all water used aboard is recycled. The water recovery system collects moisture from exhaled breath and perspiration, condensing it from the cabin air, and processes it along with urine through a series of filtration and treatment stages until it meets drinking water standards. The result of this system, astronauts consume water that was in a recent prior cycle their own and their crewmates' biological waste, is something most crew members acknowledge with a certain equanimity after a short adjustment period. The water produced is chemically pure and safe, often of higher quality than municipal tap water. The efficiency of the system is remarkable. The ISS recovers approximately 90 to 93% of the water used aboard, a closed-loop achievement that has direct implications for the design of life support systems on future deep space missions. Personal hygiene in microgravity requires a complete rethinking of every familiar process. Showering as it exists on Earth, standing under falling water is impossible. When water does not fall, astronauts wash using rinseless soap and wet washcloths, carefully applying water from sealed pouches and wiping the surface clean, collecting the moisture before it can drift away and become a hazard. Hair washing follows a similar pattern. A small amount of water is worked into the scalp, no rinse shampoo is applied, and the result is told away. Brushing teeth is manageable, though toothpaste must be swallowed rather than spat, or spat into a cloth, because a sink with running water and drainage does not exist. The toilet is a suction device that uses airflow rather than gravity to direct waste into collection containers, and its use requires familiarity and some practice. Every act of personal care that relies implicitly on gravity having a direction must be reimagined from first principles. The ISS is not a quiet place. This surprises many people who imagine space as a domain of perfect silence. But the station's interior is filled almost constantly with the sounds of machinery, fans circulating air through the environmental control systems, that pumps moving fluid through thermal regulation loops, the hum of computing equipment, and the subtle structural sounds of a large metallic vessel expanding and contracting as it passes through the heating and cooling cycle of orbital day and night. Acoustic measurements within the station have recorded average noise levels comparable to a moderately loud office environment, and in some modules higher. Crew members sleep with earplugs. Long-duration residents often describe the silence of returning to Earth as one of the most striking sensory experiences of re-entry, not the noise of the capsule or the crowd on the recovery vessel, but the first moment of standing outside under an open sky. where the sounds of wind and birds and the distant settling of the ground and the machinery has finally, after months, been left behind. Looking out the window of the International Space Station is perhaps the most transformative available experience in the known human repertoire. The cupola module, a 7-windowed observatory attached to the Earth-facing side of the station, provides a nearly panoramic view of the planet below and the space around it. Astronauts speak of spending their free time at the cupola windows, watching weather systems and river deltas and mountain ranges passing below, identifying cities by the patterns of their lights at night, watching the Terminator line divide day from night in slow, enormous motion. The sun in space has a quality that is different from sunlight seen through an atmosphere. It is harsher, unfiltered, burning white against the absolute black of the surrounding void. Stars, by contrast, do not twinkle in space. Without an atmosphere to scatter and distort their light, they appear as fixed, hard, unwavering points, more real, somehow, than they appear from the ground. Fluid behavior in microgravity is profoundly different from anything in everyday earthly experience, and astronauts working with liquids must account for this constantly. Water released from a container in microgravity does not pour, it forms a sphere, pulled inward by surface tension, with no gravitational force to elongate it into a stream or spread it across a surface. These spheres can be batted around the cabin like soap bubbles, and video of astronauts playing with floating water spheres in space has become one of the most universally delightful categories of orbital footage. Blood and other bodily fluids follow similar physical rules internally. Fluid that normally pools toward the legs under gravity redistributes toward the upper body and head in microgravity, causing facial puffiness and nasal congestion in most astronauts. During the early days of a mission, the body adjusts, reducing plasma volume, recalibrating fluid regulation. But the redistribution never fully reverses for as long as the person remains off Earth. Time on the International Space Station has a quality that long-duration crew members often describe as difficult to convey. It is simultaneously very structured and very unmoored. The daily schedule is managed in fine detail, every hour scheduled, every experiment and maintenance task and exercise session assigned to a specific time slot. Because without that structure, the absence of natural day and night, the constancy of the environment, and the subtle cognitive effects of isolation and microgravity would erode the crew's sense of temporal order. And yet, within that structure, time seems to behave strangely. Days feel both very short and very long. A 6-month mission, which seems interminable from Earth, is often reported by crew members to have felt like it collapsed to a much briefer subjective duration. The saneness of the environment, the repetitive rhythm of the schedule, the lack of the seasonal and social cues that mark time for people on Earth. All of these contribute to a peculiar temporal flatness that is one of the defining psychological features of long-duration spaceflight. At the end of a shift, when the lights in the crew modules dim to their sleep cycle setting and the bustle of experiment operations and communications with mission control quiets for the night, the ISS settles into something close to stillness. The machinery continues its hum. The fans continue their circulation. That the human activity pauses, and in the sleeping quarters, 6 or more human beings float gently in their tethered bags, arms drifting upward, breathing slowly in recycled air that was processed and cleaned and returned to them by systems they trust completely because they have no other choice. Below them, 400 kilometers below, rushing past at 8 kilometers every second, the Earth turns, Cities pass in long, glittering arcs. Oceans absorb the starlight that the cities don't consume. The thin blue line of the atmosphere holds its position against the dark, patient and luminous, a skin of gas that has kept everything living safe for billions of years. Up here, the crew sleeps. Down there, the world continues. Both are somehow at rest. The psychological screening process for astronauts is among the most thorough and demanding of any profession on Earth. Candidates undergo multiple rounds of clinical interviews, psychiatric evaluation, personality assessments, and simulated stress testing over many months. What the evaluators are looking for is not the absence of emotion or vulnerability. A person who claims to feel nothing under pressure is a person who is either performing or unaware of themselves, neither of which is desirable in a crewmate. What they are looking for is emotional regulation, the capacity to feel fear, frustration, grief, or loneliness, and to continue functioning effectively, maintaining judgment and communication and collaborative capability while those feelings are present. The ability to tolerate ambiguity, to delay gratification indefinitely, to find meaning in repetition. These qualities are weighted heavily. They are the inner resources that make long-duration spaceflight genuinely survivable at a psychological level, not merely at a physiological one. One of the most consistently reported psychological challenges of long-duration spaceflight is what researchers call sensory monotony, the cumulative effect of spending months in an environment that looks, smells, sounds, and feels almost identical every single day. The walls of the ISS modules are a consistent off-white. The air temperature and humidity are held within a narrow, comfortable range at all times. The background sounds are the same fans, pumps, and ventilation flows day after day. There are no seasons, no weather, no unexpected sensory events of the kind that make earthly days feel distinct from one another. The human brain, which is built for novelty and contrast, finds this sameness gradually wearing. Crew members report that they begin to crave variety in ways they did not anticipate. Before launch, a particular food, a different smell, the sound of wind or rain, the feel of sun on skin. These cravings are not dramatic, but they accumulate, pressing gently on the quality of daily experience over months. Communication with Earth is available to ISS crew members in ways that were not possible for earlier generations of space travelers. Video calls, email, social media, occasional private satellite calls. That this connectivity, valuable as it is, cannot substitute for physical presence. The experience of being separated from family by 400 kilometers of vacuum and all the logistics of crewed spaceflight is one that most astronauts describe as the hardest part of a mission. Significant events. A child's birthday, a parent's illness, a friend's wedding, occur on Earth without them, sometimes without the possibility of being present, even psychologically in real time. The emotional labor of maintaining relationships across that separation, of watching life continue on the surface from a distance you cannot close, is quiet and constant. Most astronauts say they manage it, and most appear to manage it with grace. But it is work, and it is never finished, and it begins the moment the rocket lifts off. Crew dynamics. The way a small group of people relate to and affect one another over months of close confinement has been a subject of scientific study since the earliest days of human spaceflight. The ISS typically houses 6 crew members in a volume roughly equivalent to a large house, but one from which no one can leave. There are no corners to retreat to, no options to step outside and take a walk. No social reset available through the ordinary mechanisms of earthly life. Research on ISS crews, as well as on analog environments like Antarctic research stations and submarine crews, consistently identifies certain social patterns. Early cohesion as the group forms and establishes its rhythms. A mid-mission period, sometimes called third quarter phenomenon, in which morale tends to dip and interpersonal friction can increase, and a late mission recovery as the end comes into focus. Mission psychologists monitor crew well-being through regular private sessions and try to support crew relationships proactively rather than reactively. Earth gazing, simply looking at the planet below from the cupola or module windows, has been documented as one of the most consistently effective psychological resources available to ISS crew members. Astronauts describe this activity as meditative, restorative, and genuinely comforting, particularly during periods of stress or low mood. There is something that appears to be intrinsically regulating about looking at the Earth from above, the familiar land masses, the recognizable coastlines, the implied presence of everyone you know somewhere within that sphere of light. Some researchers have connected this to the overview effect, the documented shift in perspective experienced when viewing the Earth from space, in which the world's divisions appear less significant and a sense of shared membership in the human enterprise becomes temporarily more available. Window time is considered important enough to the crew's psychological health that it is sometimes informally scheduled into the workday as a protected period of observation and reflection. Communication delays. The time required for a signal to travel from a spacecraft to Earth and back becomes significant on missions beyond Earth orbit, and will define the psychological texture of future deep space missions in ways that ISS crews do not experience. At the distance of the Moon, the round-trip communication delay is roughly 2.5 seconds, noticeable but manageable. At the distance of Mars, the delay ranges from about 6 minutes, when Mars is at its closest approach to Earth, to about 44 minutes, when the planets are on opposite sides of the Sun. A conversation is not possible across this delay. A question asked receives an answer 12 to 88 minutes later. A temporal gap that changes the psychological texture of every interaction with Earth, making real-time support from mission control impossible, requiring crews to be more autonomous in decision-making, and fundamentally altering the nature of the relationship between the crew and the people who support them from the ground. In the history of crewed spaceflight, there have been well-documented instances of crews pushing back against mission control, asserting boundaries, refusing tasks, reducing communication, in what researchers describe as the emergence of crew autonomy and territory in the face of excessive external management. The most famous instance involved the Skylab 4 crew in 1973, who took an unscheduled rest day without informing mission control and reduced radio contact for a period during their mission. The incident was widely characterized at the time as a mutiny, a framing that most historians and psychologists now consider overly dramatic. But it reflected a genuine tension between the pace of work demanded by mission controllers on the ground and the lived experience of fatigue and pressure aboard the station. The lesson it taught was lasting. Crew well-being, autonomy, and the right to adequate rest are not luxuries to be scheduled around operational demands. They are mission-critical resources. Sleep quality in space is measurably affected by the psychological demands of the environment, not merely the physiological ones. EEG studies of astronauts sleeping in orbit have shown that total sleep time is often shorter than before the mission, and sleep efficiency the proportion of time in bed actually spent asleep is frequently lower. Anxiety about mission performance, the hum of machinery, interrupted circadian rhythms, and the subtle but persistent unease of living in a potentially hazardous environment all contribute. Many crew members use sleep medications at some point during a mission, with approval from flight surgeons. Not chronically, but during particularly demanding mission phases or periods of elevated stress. The irony of the insomniac astronaut, a person living the dream of a generation, unable to sleep because of the accumulated weight of the experience, is one of the quieter, more humanizing details of the history of human spaceflight. The body and mind do not simply follow where ambition leads. The experience of returning to Earth after a long-duration mission involves a period of psychological readjustment that is not always discussed alongside the more visible physical recovery. Astronauts returning after 6 months or more often report difficulty with the pace and complexity of earthly environments. The noise, the crowds, the constant sensory input, the sheer number of decisions that ordinary daily life generates compared to the structured simplicity of orbit. Some describe feeling temporarily overwhelmed in grocery stores, overstimulated by conversations that involve multiple people speaking, or quietly alienated from contexts that were familiar before the mission. This transitional state is temporary. Most crew members reintegrate fully within weeks, but it speaks to how profoundly the experience of living in space reshapes the nervous system's baseline expectations. The person who returned from orbit is the same person who left, and yet has been changed quietly by months of a kind of living that no one on the ground has shared. Personal rituals play an outsized role in the psychological life of astronauts on long missions. Many crew members maintain daily practices, journaling, specific music listened to at particular times of day, photographs arranged in the crew quarters, small objects carried from Earth as talismans that perform a function far beyond what their physical presence suggests. These rituals are anchors, stable, self-chosen structures within a profoundly controlled external environment, acts over which the individual has personal authority in a life that is otherwise scheduled to the minute by mission controllers on the ground. The human need for personal territory and self-expression does not diminish in space. It becomes, if anything, more acute. Astronauts are permitted a small personal preference kit, a container of items brought from home at crew discretion, within strictly regulated mass limits. And the choices people make about what to include in this limited space reveal something true and particular about what they hold most important. Boredom, rarely discussed in the romanticized public narratives of space exploration, is a genuine feature of long-duration missions. The daily schedule is demanding, but unscheduled time exists, and the entertainment options aboard the ISS, while reasonable, are finite. Books, films, music, video calls with family, occasional live interactions with schools and media. After months, repetition sets in. The resolution to this problem for most long-duration crew members is one of the oldest available to anyone in a confined or monotonous situation, turning inward. Astronauts in long interviews often describe a deepening of their interior lives during extended missions. More reflection, more attention to the present moment, a quality of attentiveness to small things that is sometimes difficult to maintain amid the pace of normal earthly life. The void outside the window and the sameness inside the modules can create, perhaps paradoxically, a kind of involuntary contemplative practice post-flight. Many astronauts report a perspective shift that persists long after the physiological recovery is complete. a lasting change in the way they relate to the scale of human concerns, to the fragility of the Earth's environment, to the significance of what divides people and what unites them. This is the long echo of the overview effect, not the immediate visual experience of seeing the Earth's curve against the dark, but the slower percolation of that experience through a whole life's subsequent context. Some veterans of long-duration spaceflight become advocates for environmental protection, or for international cooperation, or for what might be broadly described as a planetary perspective, a way of seeing human activity from the outside, rather than from within it. The mission ends, the rocket lands. The body recovers, but the memory of having looked at the entire world through a small window at 400 kilometers of altitude, and of having found it small and bright and precious and whole, that does not entirely leave. It goes into the background of everything that follows, and it stays there. The innermost layer of a spacesuit, worn directly against the skin, is a liquid cooling and ventilation garment. A close-fitting undersuit laced with a network of small-diameter tubes through which cool water is continuously circulated. The purpose of this layer is thermal management from the inside out. The body generates heat during the physical exertion of a spacewalk, and without active cooling, the interior of a sealed suit would rapidly become dangerously hot. The cooling water carries that heat outward to the suit's thermal management system. Where it is radiated into space, the garment also provides ventilation, moving oxygen-enriched air across the skin to prevent localized hotspots and ensure gas circulation around the entire body. Together, these two functions, liquid cooling and gas ventilation, form the first line of thermal protection in the suit, managing the considerable heat generated by a human being working hard in a garment that is, by necessity, sealed completely against its environment, the pressure garment. The layer that contains and maintains the suit's internal atmosphere is one of the most mechanically challenging elements to design. It must hold a positive pressure of about 4.3 pounds per square inch above the vacuum of space, which means it is constantly being inflated outward against the pull of the vacuum outside. An inflated tube resists bending. An inflated sphere resists any change in shape. Without careful engineering, a pressurized suit becomes rigid and nearly impossible for the wearer to move in. A balloon shaped vaguely like a human, the arms and legs stiff and resistant. Work all but impossible. Modern pressure garments use a combination of geometric patterning, special restraint cables, and carefully engineered convolutes, accordion-like folded joints at the shoulders, elbows, wrists, hips, knees, and ankles that allow flexion and extension despite the internal pressure. The result is a garment that remains wearable and functional, though always with a subtle resistance that makes physical work in a spacesuit consistently more demanding than the equivalent task without one. Outside the pressure garment lies a series of additional protective layers collectively called the thermal micrometeoroid garment, or TMG, the suit's outermost shell visible in photographs as the white quilted exterior of a typical NASA spacesuit. This layer has two distinct functions: protection against micrometeoroids and orbital debris, and thermal insulation against the extreme temperature swings of the space environment. In direct sunlight, the outer surface of a spacesuit can reach temperatures above 120 degrees Celsius. In shadow, it can drop to below -150 degrees Celsius, this temperature range. A swing of nearly 300 degrees occurs repeatedly during a single spacewalk as the astronaut moves between sunlit and shadowed regions of the spacecraft. The TMG's multiple layers of aluminized mylar, dacron, and other specialized materials reflect solar radiation, insulate against conductive and radiative heat loss, and provide a modest shield against small, high-velocity particle impacts that would otherwise penetrate to the pressure garment beneath. The gloves of a spacesuit are, by many accounts, the component that defines the suit's usability more than any other. A suited astronaut working outside a spacecraft must be able to manipulate tools, turn fasteners, grip handrails, handle wire connectors, and perform fine motor tasks requiring significant dexterity, all while wearing heavily insulated gloves that enclose a pressurized interior and maintain thermal protection for the hands in an environment where bare skin would suffer frostbite or thermal burns within seconds depending on solar exposure. The engineering of spacesuit gloves involves layering that maintains warmth and pressurization without eliminating tactile feedback, using palm bar restraints to reduce the inflated stiffness of the fingers and heating elements in the fingertips to guard against cold injury during shadowed work. Despite these measures, astronaut hand fatigue during long EVAs, extravehicular activities, the formal term for spacewalks, is one of the most commonly reported physical discomforts, and hand injuries are among the most frequent medical issues associated with spacewalk operations. The helmet of a modern spacesuit is not simply a clear bubble over the head. It is a complex optical and protective system. The polycarbonate pressure helmet creates the closed atmospheric environment around the head, but over it sits a separate visor assembly containing multiple layered visors with different protective functions. The gold-coated outer visor reflects solar infrared and ultraviolet radiation, preventing both thermal heating and radiation damage. It is the gold visor, pulled down in iconic photographs of astronauts in sunlight, that gives the standard image of an EVA suit its distinctive color. Inside the visor assembly are additional layers that protect against micrometeoroid impact and provide a small degree of redundancy. If the outer visor is struck and cracked, the inner visor layers maintain the sealed atmosphere. The helmet also incorporates a feed port for water, a small straw accessible within the helmet from a water bag in the suit's upper torso, allowing the astronaut to drink during a spacewalk that may last 6 to 8 hours. The life support system that keeps an astronaut breathing during a spacewalk is housed in the primary life support system, a backpack-mounted unit attached to the rear of the hard upper torso of the suit. This unit contains the oxygen supply for breathing, the carbon dioxide removal system, which uses lithium hydroxide canisters to chemically absorb exhaled CO2, the water supply for cooling the communications equipment, and the power supply for electronics and fans. The PLSS is designed for a nominal EVA duration of 6 to 8 hours, with a safety margin that allows for contingency extensions. Carbon dioxide removal is one of the most critical functions. The atmospheric concentration of CO2 rises rapidly in a sealed environment where a person is breathing, and without active removal, it would reach incapacitating levels within an hour. The lithium hydroxide canisters have a finite capacity, and monitoring their saturation is one of the ongoing background tasks of any spacewalk timeline. Astronauts performing spacewalks outside the International Space Station wear, clipped to the back of their suits, a unit called the Simplified Aid for EVA Rescue. SAFER, a small self-contained maneuvering device that can be activated in an emergency. If an astronaut were to become detached from the station and begin drifting away, severed from the safety tether that normally keeps them connected to the structure, SAFER provides a brief, limited ability to maneuver back to the station using cold gas nitrogen thrusters arranged around the unit's frame. Safer is not a primary propulsion system and carries only enough propellant for a few minutes of controlled flight. Its role is entirely contingency, to give a separated astronaut the possibility of returning to the station rather than drifting silently away into orbital space. It has never been used in a real emergency, and every astronaut who wears it during a spacewalk hopes it stays that way. It is insurance against a scenario that no operational procedure is designed to allow. The duration of a spacewalk is limited primarily by the consumables carried in the primary life support system, the oxygen and the CO2 absorption capacity, and by human physiology. 6 to 8 hours is the standard operational limit, and even within that range, the physical demands are considerable. Moving in a pressurized suit requires significantly more muscular effort than the same movements without it. Gripping tools, maneuvering along handrails, and anchoring the body in position against the tendency to float away from surfaces all generate sustained physical loading. At the end of a long EVA, most astronauts return to the airlock, fatigued in a way that is distinctive. Not the exhaustion of running, but the deeper, more diffuse fatigue of hours of sustained fine motor effort under resistance, the muscles of the hands, forearms, and core having borne most of the work. The airlock repressurization that signals the end of the spacewalk is, by most accounts, a profoundly welcome sound, the slow return of the worlds inside the walls. The design of next-generation spacesuits for Artemis lunar surface operations and eventual Mars exploration has moved toward improved mobility, reduced mass, and greater ease of donning and doffing compared to the legacy designs that served the ISS program. The Axiom Extravehicular Mobility Unit, Axiom-U, and NASA's Axiom-U suit concepts both incorporate improved bearing joints at the shoulder and hip that dramatically reduce the effort required to move against suit pressure, lower torso assemblies that allow more natural walking gaits for planetary surface work, and helmet designs with wider fields of view to improve situational awareness in complex terrain. Suits designed for Mars must also contend with that planet's thin CO2 atmosphere and its fine, abrasive dust, a particulate hazard that poses risks to seals, visors, and mechanical components throughout the suit's operational life. The spacesuit of the future is not simply an improved version of what came before. It is a fundamentally different design problem, posed by a fundamentally different destination. Suit fit is among the most underappreciated technical challenges in spacesuit engineering. The human body changes shape in microgravity. The spine lengthens as the discs decompress without the loading of gravity, and overall height increases by 1 to 2 inches in the early weeks of a mission. A suit fitted on the ground before launch may no longer fit the same astronaut correctly after weeks in orbit, with potential consequences for comfort, mobility, and in extreme cases, safety. The ISS uses a modular sizing approach. The suit's components can be mixed and matched from a range of sizes to accommodate different body proportions. But the available range still does not accommodate all body types and sizes, a limitation that has historically been more restrictive for smaller statured candidates. Addressing this and moving toward fully adjustable or custom-fitted suit systems is one of the design priorities in the development of the next generation of hardware. The emotional experience of a spacewalk, as described by virtually every astronaut who has performed. 1. Occupies a place in the range of human experiences that has no obvious earthly equivalent. You are outside, not outside a building, not outside a country, but outside the planet, separated from the entirety of Earth's atmosphere by a few layers of carefully engineered polymer and metal, surrounded by a vacuum that extends in every direction for distances that make the imagination stall. And it is quiet. Whatever sounds exist are internal to the suit. The hum of the fans, the whisper of oxygen flow, the soft sound of your own breathing amplified within the helmet. The vast silence outside the suit is total and absolute, because sound requires a medium to travel through and there is none. Below, the earth turns. Above, in every direction except below, the stars hold their positions, unwavering, in a blackness that has no edges and no end. Most astronauts describe this moment, the first time they float fully outside, as the single most vivid experience of their lives. Some describe it as a kind of prayer. None of them have words for it that feel quite adequate. When a spacewalk ends and the airlock is repressurized, the atmosphere that floods back in carries something the suited astronaut has not encountered for 6 or 8 hours: smell. Space itself has no smell. A vacuum contains nothing to carry scent molecules to an olfactory receptor. But the suit and the metal and composite materials of the spacecraft's exterior carry trace molecules on their surfaces that become volatile in the vacuum and condense again when atmosphere returns. Astronauts consistently describe a distinctive smell associated with returning from a spacewalk and with the materials used on the exterior of the ISS, a metallic, slightly sharp, ozone-like quality, sometimes compared to the smell of struck metal or spent fireworks. No one has successfully identified the precise chemical compounds responsible, and the description varies between individuals. But it is consistent enough and distinctive enough that it has become one of the small sensory footnotes of the history of spacewalking. The smell of the outside of the world, carried back in on the surface of a glove. The distance between Earth and Mars is not fixed. Both planets orbit the Sun, and their relative positions change continuously as they travel their respective paths. At closest approach, called opposition, Mars can be as near as about 55 million kilometers from Earth. At its most distant, when the two planets are on opposite sides of the Sun, that separation expands to over 400 million kilometers. Most realistic mission architectures plan to launch during favorable windows near opposition, when the energy required to make the transit is minimized. Even then, a one-way journey from Earth to Mars using conventional chemical propulsion takes approximately 7 to 9 months, half a year or more of transit through the deep interplanetary medium, far from any resupply or rescue capability, with the crew entirely dependent on the systems aboard the transit vehicle and the consumables those systems can carry. The transit is the first thing, and it is already a significant thing. The radiation environment during a transit to Mars is one of the most serious medical risks of any crewed Mars mission, and it is one that current technology addresses only partially. Within Earth's magnetosphere, astronauts are shielded from most high-energy cosmic rays and solar energetic particle events by the planet's magnetic field. Beyond that protective bubble in the deep interplanetary medium, that shielding disappears entirely. Galactic cosmic rays, high-energy particles originating from outside the solar system, accelerated by supernova remnants and other energetic events, penetrate the thin walls of a spacecraft continuously, passing through the hull and through the bodies of the crew, depositing ionizing radiation in tissues and DNA along the way. Estimates suggest that a 6 to 9 month transit to Mars, plus time on the Martian surface and the return journey, would expose a crew to radiation doses at or beyond current career limits for ISS astronauts. significantly increasing the lifetime risk of radiation-induced cancers. The Martian atmosphere, while present, is not breathable by humans and would not protect a person on the surface from radiation in the way Earth's atmosphere does. Mars's atmosphere pressure at the surface averages about 0.6% of Earth's at sea level, thin enough that it would be lethal to an unprotected human in seconds, not because of toxicity, but because the pressure is far below what is needed to keep the body's fluids from boiling at body temperature. The atmosphere is composed primarily of carbon dioxide, with small amounts of nitrogen, argon, and trace gases. It is too thin to provide meaningful radiation shielding. The total atmospheric depth on Mars is roughly comparable to being at an altitude of 30 kilometers on Earth, above most of the shielding that Earth's atmosphere provides. Settlers on Mars will need pressurized habitats, sealed suits, and either underground living quarters or significant shielding above ground to manage the chronic radiation exposure of surface life. Martian dust is both one of the most visually striking features of the planet and one of the most practically challenging for any long-duration surface mission. Mars experiences regional and occasionally global dust storms, episodes in which fine, electrically charged dust particles are lifted into the atmosphere and can remain suspended for months, reducing sunlight to the surface and coating solar panels, equipment, surfaces, and airlock seals. The dust itself is chemically problematic. Martian soil contains perchlorates, chlorine-containing compounds that are toxic to humans in significant concentrations and could be carried into habitats on the surfaces of suits and equipment. The particle size of Martian dust is very fine, comparable to flour, which makes it clingy, difficult to remove from surfaces, and potentially hazardous to respiratory systems if habitats are contaminated. Engineering around Martian dust, seals, filtration systems, airlock designs, dust removal mechanisms will be one of the quieter but more persistent challenges of any sustained surface presence. Growing food on Mars will be an eventual necessity for any long-duration settlement, both for caloric sustenance and, perhaps more importantly, for the psychological value of interacting with living, growing things in an environment that is otherwise entirely artificial. The Martian soil, called regolith, is not inherently fertile. It lacks the organic material and biological activity of Earth soil, and its perchlorate content would need to be chemically remediated before plant cultivation could begin. Initial approaches would likely involve closed-loop hydroponic or aeroponic growing systems, plants grown in nutrient-rich water or misted with nutrient solutions, with no reliance on the regolith at all. Light must be supplemented artificially, because the solar irradiance at Mars is roughly 43% of what Earth receives, and dust storms reduce it further. The energy costs of artificial lighting for crop growth are substantial, and the species of plants suitable for closed environment cultivation, leafy greens, legumes, root vegetables, would form the practical core of a Martian agricultural repertoire. The concept of terraforming Mars, transforming it over very long timescales into a more Earth-like environment, sits at an interesting boundary between serious scientific speculation and genuine engineering theory. The broad outlines of what would be required are understood. Mars would need a thicker atmosphere, higher surface temperature, and protection from solar wind erosion to sustain liquid surface water and eventually support an unprotected biosphere. Various proposals exist for achieving these conditions. Releasing CO2 from Martian polar ice caps through targeted heating, seeding the atmosphere with manufactured greenhouse gases, redirecting volatile-rich asteroids to impact the surface. but each requires energy or time or both at scales that dwarf any current human engineering effort. The minimum timescale for meaningful terraforming, under even optimistic assumptions, is measured in centuries to millennia. Generation-spanning civilization committed to planetary transformation over timescales longer than recorded human history. It is an extraordinary idea to carry into sleep in situ resource utilization. ISRU in the engineering shorthand is the principle of using materials found at the destination to manufacture the resources a mission needs, rather than bringing everything from Earth. For Mars, ISRU is not a luxury. The sheer mass of supplies required to sustain a crew on Mars for an extended period makes it physically impossible. At current projections to bring everything needed from Earth, the cost and mass constraints of launch and transit are simply too severe. The Martian atmosphere, predominantly CO2, can be processed to produce breathable oxygen and the methane propellant needed for a return vehicle. A process already demonstrated in miniature by NASA's MOXIE instrument aboard the Perseverance rover, which produced oxygen from Martian CO2 in 2021. Water ice, confirmed in significant quantities below the Martian surface and in polar deposits, can be extracted and electrolyzed into hydrogen and oxygen. These local resources, if reliably accessed, change the arithmetic of Mars missions fundamentally. The Martian day, called a sol, is remarkably close in length to an Earth day: 24 hours, 39 minutes, and 35 seconds. This near coincidence is one of the more accommodating aspects of the Martian environment for human habitation, at least biologically. 4. Human circadian rhythms calibrated to a day of roughly this length would not require the same aggressive artificial management that orbit's 92-minute day-night cycle demands. Martian sunrise and sunset, filtered through the thin atmosphere with its fine dust, would appear in distinctive hues, the sky near the horizon tinted blue at sunrise and sunset, a reversal of the earthly experience, while the daytime sky ranges from a pinkish tan to a butterscotch, depending on dust loading. Gravity on Mars is approximately 38% of Earth's. Enough to keep things on floors and liquids in containers, enough for the body not to face the full deconditioning of microgravity, but low enough that the long-term effects on bone and muscle are still a subject of genuine physiological concern. The psychological isolation of a Mars mission will differ from ISS operations, not merely in degree, but in kind. ISS crew members, at 400 kilometers altitude, are separated from Earth by a gap that their own eyes can bridge. They can see the planet, they can communicate with it in real time, they could in principle be returned to it within hours in an emergency. Mars crew members will be separated from Earth by a gap that communications take 6 to 44 minutes to cross each way. That requires a transit of 6 to 9 months to close in either direction. And that makes emergency return, in all realistic mission architectures, an option that is simply not available. If something goes wrong on the surface of Mars, the crew will handle it themselves, or it will not be handled. The psychological weight of that situation, genuine unqualified self-reliance at interplanetary distance, will require a quality of inner stability and group cohesion that even the most demanding ISS mission does not fully approach. What a Martian habitat might actually look and feel like to live in is a subject that designers and architects have given careful thought, recognizing that the psychological dimensions of habitat design are as important as the structural and engineering ones. Early habitats will almost certainly be compact, functional, and densely equipped, inflatable modules, prefabricated structures, or lava tubes sealed and pressurized, with the premium of livable volume pressing against the mass constraints of what can be sent from Earth. Windows, if present, will be small and triple-layered, offering a view of a landscape that is red and rocky and compelling, but also monotonous in its geological scale. As settlements mature and become more self-sustaining, interior spaces are expected to expand. Common areas with plants and varied lighting and social gathering spaces appear in nearly all long-duration habitat design concepts, because the designers understand that people living in a sealed environment for years need space to feel like something more than survival. The selection and training of the first people to live on Mars permanently, if such a mission occurs, will represent a human selection process unlike anything in history. They will be asked to leave, with the strong probability of never returning, the only planet in the universe known to harbor life, the only world any human being has ever lived on. They will be asked to build a civilization in its earliest and most fragile form, in an environment that is actively hostile to biological life, with limited support from Earth and no guarantee that the next supply ship will arrive on schedule. Every skill they possess will matter. Every relationship they maintain with their crewmates will matter. Their capacity to find meaning in the long, difficult, repetitive, isolated work of planetary survival will matter immensely. Who those people will be, what experiences and temperaments and values shape them, is one of the more profound human questions embedded in the practical engineering problem of going to Mars. Mars has two small moons, Phobos and Deimos, both irregularly shaped, both thought to be captured asteroids, and both orbiting in ways that make them unusual neighbors. Phobos orbits Mars faster than the planet rotates, completing an orbit in just 7.65 hours, meaning that from the Martian surface, it rises in the west and sets in the east, twice per Martian day. It is also slowly spiraling inward due to tidal deceleration, and is expected to either impact Mars or break apart into a ring system within the next 30 to 50 million years. Deimos, the smaller of the two, orbits much further out and moves more slowly. To a person standing on the Martian surface, both moons would appear small. Phobos, roughly 1/3 the angular size of Earth's moon as seen from Earth. Deimos barely distinguishable from a bright star. They are not the grand companion that Earth's moon is, but they will be there, moving across that butterscotch sky, and they will be the moons of home. Sound, in the physical sense, is a pressure wave, a propagating oscillation of compression and rarefaction moving through a medium. It requires molecules to transmit. When a source vibrates, it pushes and pulls on the molecules immediately adjacent to it, which push and pull on the next layer, and the disturbance travels outward through the medium at a speed determined by that medium's density and elasticity. In space, in the near vacuum of the interplanetary medium, the density of particles is so vanishingly low that no such propagation is possible on any humanly relevant timescale or scale. A rocket engine firing in space is, from outside the vehicle, completely silent. An explosion aboard a spacecraft would produce no sound in the surrounding space. The entire history of our solar system, 4.5 billion years of planetary collisions, solar flares and asteroid impacts, has unfolded in an environment where every violent event that occurred away from a planetary atmosphere did so in complete, unbroken silence. The interplanetary medium, the space between the planets, is not truly empty, but its contents are extraordinarily sparse by any earthly comparison. The solar wind, a continuous stream of charged particles, primarily protons and electrons, expelled from the Sun's outer atmosphere at speeds of 400 to 800 kilometers per second, fills the interplanetary medium with a tenuous plasma flowing outward in all directions. The density of this solar wind at Earth's solar distance is roughly 5 to 10 particles per cubic centimeter. To put this in perspective, the air you are breathing contains approximately 27 billion molecules per cubic centimeter. The solar wind carries with it the Sun's magnetic field, stretched into a vast spiral pattern called the Parker spiral by the combination of solar rotation and outward flow. This magnetic structure threads through the entire solar system, connecting every planet to the Sun through invisible field lines that guide energetic particles across hundreds of millions of kilometers of space. The thermal environment of space, the temperatures experienced by objects in the interplanetary medium, is governed not by convection or conduction, but almost entirely by radiation. There is no air to carry heat from one place to another. An object in space heats up by absorbing electromagnetic radiation from the Sun and cools by radiating its own thermal emission into the surrounding void. At Earth's distance from the Sun, a non-reflective object would stabilize at a temperature of roughly -3 degrees Celsius. Cold, but not catastrophically so. Much closer to the Sun, objects heat dramatically. At Mercury's distance, the sunlit surface reaches over 430 degrees Celsius. In the deep outer solar system, beyond Pluto, objects cool to temperatures within a few dozen degrees of absolute zero. A spacecraft transiting between the planets must manage this radiative environment carefully, maintaining internal temperatures within narrow operational ranges, using insulation, passive radiators, heaters, and careful orientation control relative to the direction of the Sun. The heliosphere, the vast bubble of influence that the Sun carves out in the interstellar medium through the constant pressure of the solar wind. The boundary where the solar wind's outward pressure finally equilibrates with the pressure of the interstellar medium is called the heliopause, and it lies at a distance of roughly 120 to 150 astronomical units from the Sun, 120 to 150 times the distance from Earth to the Sun. This boundary marks the edge of the Sun's direct physical influence over the surrounding space. Inside the heliopause, the solar wind dominates. Outside it, the interstellar medium, the material between star systems, prevails. 2 spacecraft have crossed this boundary. Voyager 1, which crossed the heliopause in 2012, and Voyager 2, which crossed it in 2018. Both were launched in 1977. Both are still operating, still transmitting data across incomprehensible distances, their signals taking more than 20 hours to reach Earth. The Voyager probes represent humanity's most distant physical presence in the universe. Voyager 1, as of the mid-2020s, is more than 23 billion kilometers. From the Sun, over 150 astronomical units, moving outward at roughly 17 kilometers per second. Despite this extraordinary distance, its scientific instruments continue to return data about the interstellar environment, detecting the density and direction of interstellar plasma and magnetic fields in a region of space no previous human-made object has ever sampled. The radio signal from Voyager 1, traveling at the speed of light, takes over 22 hours to reach Earth. Engineers at NASA's Jet Propulsion Laboratory communicate with both Voyagers through the Deep Space Network, a system of large dish antennas distributed around the world, receiving signals so faint that the power arriving at the antenna is less than a billionth of a watt, requiring extraordinary amplification before the data can be read. The golden record aboard each probe carries sounds and images of Earth, a message addressed to no one in particular, carried outward into the dark. The interplanetary space through which any Mars-bound spacecraft must pass contains not only the solar wind plasma and magnetic field, but also a sparse population of dust grains. The interplanetary dust complex, derived from comets shedding material as they approach the Sun, and from collisions between asteroids in the main belt. These dust particles are distributed throughout the inner solar system in a broad plane, roughly aligned with the ecliptic, and they scatter sunlight to produce the zodiacal light, a faint, diffuse glow visible along the ecliptic from Earth, on very dark nights, extending upward from the horizon, after sunset or before sunrise. To a spacecraft transiting the inner solar system, these particles pose a low but non-zero impact risk. At relative velocities of tens of kilometers per second, even a particle of a few micrograms carries significant kinetic energy. Spacecraft hulls are designed to withstand small impacts, but the cumulative erosion over years and the occasional larger grain represent genuine hazards of long-duration interplanetary travel. Microgravity in transit. During the long coast phase of a journey between planets, after the propulsion system has finished its burn and before arrival at the destination, is as complete as anything found in Earth orbit. With no planetary body close enough to generate a locally significant gradient in gravitational pull, a transit spacecraft and everything inside it falls freely through the solar gravitational field in a path described by orbital mechanics. The crew floats. Every loose object floats. The ship's trajectory is a long, graceful arc through the inner solar system, governed entirely by the initial velocity imparted by the departure burn and the subtle, continuous influence of the Sun's gravity. Small trajectory correction maneuvers, brief engine firings to adjust course as navigational measurements accumulate, are the only interruptions to this long free fall, each lasting only minutes and producing only small velocity changes, too gentle to register as anything dramatic against the background of months of weightless coasting through the deep, patient silence. The psychological texture of interplanetary transit, 6 to 9 months of coasting through the emptiness between Earth and Mars, with the Sun diminishing behind and the red point of Mars growing ahead, Earth receding to a small bright dot, then a dim one, is something no human being has yet experienced, and its full shape can only be imagined from what we know of analogous situations. The submarine service, Antarctic overwinter stations, and long-duration ISS missions offer partial templates, but none quite matches the combination of distance, isolation, and permanence of direction that a Mars transit involves. The crew will have turned their backs on Earth, irreversibly, in a way that ISS astronauts never must. The blue-white point in the rearward direction will shrink for months and months until it becomes one bright object among thousands. And ahead, the rust-colored point will grow, slowly, then less slowly, until it becomes a disk, and then a world, filling the window, a destination finally arriving after a journey no shorter than it needed to be. The vacuum of space has a precise scientific definition. It is a region where the pressure is lower than atmospheric pressure on Earth. But the word vacuum, as used in the context of deep space, refers to something far more extreme, pressures so low that they are almost incomparable to anything achievable in a laboratory environment. The interplanetary medium has a pressure of roughly 10 pascals, compared to Earth's standard atmospheric pressure of roughly 101,325 pascals. The best vacuum chambers on Earth, used for testing spacecraft components and simulating the space environment, cannot fully replicate this. Even the finest laboratory vacuum contains more molecules per cubic centimeter than the interplanetary medium at Earth's orbit distance. This extreme vacuum has practical consequences for materials. Substances that would not evaporate on Earth can vaporize slowly in high vacuum, lubricants behave differently, and polymers used in insulation can outgas, releasing molecules that may contaminate sensitive optical or scientific surfaces on the spacecraft in the vicinity of a planet with a magnetic field. Earth, Jupiter, Saturn, the solar wind interacts with that field to form a magnetosphere, within which charged particles are trapped and guided along field lines. Earth's magnetosphere extends roughly 60,000 kilometers toward the Sun and stretches far downwind in a long magnetotail. Within it, the Van Allen radiation belts, two donut-shaped regions of trapped high-energy particles, encircle the planet at altitudes between roughly 1,000 and 60,000 kilometers. Spacecraft transiting from low Earth orbit to the open interplanetary space must pass through these belts, and crewed spacecraft are designed to transit them as quickly as possible to minimize radiation exposure. The Apollo missions, for example, crossed the Van Allen belts rapidly during their translunar injection burns, spending only a few hours in the most intense regions, a trajectory choice motivated as much by radiation protection as by orbital mechanics. The silence of space, so total and so absolute, is nevertheless full of signals invisible to human senses. Radio waves from pulsars sweep past in periodic pulses. Microwave radiation from the Big Bang. The cosmic microwave background arrives from every direction in the sky with extraordinary uniformity, a whisper from 380,000 years after the uniformity. A whisper from 354 here, a few extraordinary uniformity. Gamma-ray bursts flash from distant galaxies, occasionally bright enough to affect the upper atmospheres of planets across cosmic distances. X-rays from neutron star binary systems pulse outward in regular clockwork rhythms. The space through which every spacecraft travels is alive with electromagnetic activity across the entire spectrum, none of it audible, most of it invisible. All of it carrying information across distances so large that the events which generated the signals may have occurred before most of the stars in our galaxy were born. The universe is extraordinarily communicative. We simply lack the biological equipment to hear what it is saying without instruments to translate for us. There is something about the concept of interplanetary space that the mind goes to willingly, even gratefully, in the quiet hours of the night. A kind of negative space in the imagination, a region of stillness and scale that allows the smaller concerns of a day to dissolve against its vastness. It is not that the problems disappear. They simply find their proper size, held against the scale of a journey that takes 9 months to complete and crosses hundreds of millions of kilometers of vacuum. Against that scale, the friction of a difficult conversation, the weight of an unresolved worry, the accumulated pressure of too much to do in too little time. These things do not vanish, but they do become proportionate. They reveal themselves as what they always were: small, temporary, solvable, or at least survivable. The void between the planets is not threatening in this frame. It is clarifying. It is generous in its scale. It offers, to the mind willing to extend into it, a very specific quality of rest. Ion propulsion, the use of electrically accelerated ions as a propellant, represents one of the most important advances in spacecraft propulsion of the past several decades, already in operational satellites. Unlike chemical rockets, which produce enormous thrust for very short periods, ion thrusters produce extremely small thrust, continuously over very long periods, gently but persistently accelerating a spacecraft in a way that, given enough time, can yield velocities far exceeding what chemical propulsion alone could achieve. The Dawn spacecraft, which orbited both the asteroid Vesta and the dwarf planet Ceres, used ion propulsion to accomplish a trajectory that would have been impossible with chemical rockets. The specific impulse of ion thrusters, their fuel efficiency, is 10 to 80 times greater than chemical engines, depending on design. Their limitation is thrust. The force produced is tiny, measured in millinewtons, and building up meaningful velocity requires months to years of continuous firing. In the patient arithmetic of interplanetary travel, this is acceptable. For interstellar travel, it is still far too slow. Nuclear thermal propulsion, an engine concept studied seriously by the United States and the Soviet Union in the 1950s and 1960s, and now being revisited by multiple space agencies. Offers a middle path between the brute thrust of chemical rockets and the high efficiency but low thrust of ion drives. In a nuclear thermal rocket, a nuclear reactor heats a propellant, typically liquid hydrogen, to extraordinarily high temperatures, and the superheated gas is expelled through a nozzle to produce thrust. The specific impulse achievable is roughly twice that of the best chemical engines, meaning the rocket is twice as propellant efficient for a given thrust level. This improvement would significantly reduce transit times to Mars and the outer planets, making missions that would take 9 months with chemical propulsion achievable in perhaps 4 to 6 months. NASA and DARPA have active programs developing nuclear thermal propulsion systems, with crewed applications to Mars cited as the primary motivation. It is not science fiction. It is funded engineering. Solar sails represent one of the most elegant propulsion concepts in the history of space engineering, exploiting a real physical force, the momentum of photons, that is freely available throughout the inner solar system and beyond. Photons carry momentum, despite having no mass, and when they reflect off a highly polished surface, they impart twice their momentum to the reflecting material. A push, however gentle. The force from sunlight on a solar sail is extraordinarily small. A sail 1 kilometer square at Earth's distance from the Sun receives a thrust of roughly 5 newtons, less than the weight of a kilogram mass on Earth's surface. But it is continuous and costs no propellant. Given months and years of uninterrupted acceleration, a sail-propelled spacecraft can build up impressive velocities. JAXA's Archaeotaurus mission, launched in 2010, was the first spacecraft to successfully demonstrate solar sail propulsion in deep space, deploying a 196 square meter sail and confirming the photon pressure acceleration predicted by theory. The concept scales, very large, very lightweight sails could in principle accelerate small payloads to a few % of the speed of light given proximity to the Sun. The Breakthrough Starshot initiative, announced in 2016 and backed by Stephen Hawking and investor Yuri Milner, proposed an approach to interstellar travel that bypasses the mass and propellant constraints of conventional spacecraft by reducing the payload to its absolute minimum. The concept involves launching a fleet of gram-scale Starship spacecraft tiny flat wafers carrying miniaturized cameras, sensors and communications equipment, attached to equally miniaturized light sails, and then accelerating them using a powerful ground-based laser array, aiming to push the nanocraft to roughly 20% of the speed of light. At that velocity, a starship could reach the Alpha Centauri system in approximately 20 years. The engineering challenges are formidable. A laser array of sufficient power would need to be orders of magnitude more powerful than any that currently exists. The sail must survive acceleration forces and interstellar dust impacts at relativistic speeds, and the nanocraft must transmit data back across 4 light-years with an antenna measured in millimeters. But none of these challenges is prohibited by physics. They are merely very difficult engineering problems. A generation ship, a spacecraft designed to carry human beings on an interstellar journey so long that the original passengers would die before reaching the destination, and their descendants would complete the voyage, is one of the most philosophically provocative concepts in the long history of thinking about space exploration. The concept requires not just engineering of unprecedented scale, but a rethinking of the social, ethical, and psychological dimensions of the journey. A generation ship is a civilization in miniature. It must produce its own food, recycle all its water and atmosphere, maintain its technology, educate its children, resolve its conflicts, and preserve the institutional knowledge required to operate the ship across generations of human turnover. The people born aboard the ship did not choose to be there. The destination they are sailing toward is not a place anyone aboard will remember leaving Earth to reach. The voyage defines their entire existence. This raises questions that engineering cannot answer, but that any serious discussion of interstellar colonization must eventually face. The interior design of a generation ship, were one ever built, would be one of the most consequential architectural problems in human history. The creation of a world that must sustain human beings physically, psychologically, and culturally across a span of decades to centuries, with no possibility of resupply or modification from outside. Nearly all serious generation ship concepts include some form of artificial gravity, most often achieved through rotation of the habitat section, with the centrifugal acceleration providing a substitute for gravitational loading on the body. The rotating habitat would need to be large enough that the Coriolis effect, the apparent deflection of moving objects in a rotating frame, does not become disorienting for the inhabitants. Theoretical habitat rings of 1/2 kilometer or more in radius, rotating at 1 to 2 revolutions per minute, could provide Earth-like gravity at their outermost rim. Agricultural zones, recreational spaces, social gathering areas, private quarters, all would need to exist within the finite and absolutely fixed volume of the ship, shared by every person born into that world for the duration of the voyage. The food and life support systems of a generation ship would need to be not merely efficient, but essentially perfect in their long-term reliability. On a Mars mission of 2 or 3 years, a life support failure can potentially be addressed by resupply, or is tolerable for the known finite duration of the mission. On a century-long interstellar voyage, a failure in the food production system, the water recycling system, or the atmosphere management system is not a problem that gets resupplied from outside. It is an existential threat to everyone aboard. The design philosophy shifts from what is reliable to what is self-repairing, what is redundant to the point of near impossibility of simultaneous failure across all redundancies, what the crew can maintain and rebuild with the materials available to them on the ship. A closed biological loop in which organism waste feeds plant growth, which feeds organism nutrition, offers the most robust template, but maintaining genuine ecological stability at small scale over centuries remains far beyond the current state of the ecological management art. The sociology of a generation ship, how a human community of perhaps hundreds to thousands of individuals would organize itself, govern itself, resolve disputes, and maintain cultural continuity across multiple generations, and psychology, none of which offers comfortable reassurances. Human groups in isolated, closed environments have consistently developed social hierarchies, factional conflicts, and cultural drift, even over spans of years, across a century or more. The social structures of the founding generation would not simply persist. They would evolve, fragment, be reinterpreted, be rebelled against, and be rebuilt by descendants who have no living memory of the world. The ship departed. The laws, the customs, the freaks, the freeze of no living memory of the world. The ship departed. The laws, the customs, the freeze of no living memory of the world. The ship departed. The freeze of no, the shared narratives, the technical knowledge required to operate the ship, all of these must somehow be transmitted and preserved across the equivalent of 3 to 4 human generations in a community that cannot recruit new members from outside and cannot expel troublesome ones. The ethical question embedded in the generation ship concept, the question of whether it is morally acceptable to bring children into existence in a situation they did not choose, aboard a ship they cannot leave, bound for a destination they will never see, is one that philosophers and ethicists have not resolved and may never fully resolve. Every human being is born into circumstances they did not choose. A particular country, family, economic situation, and set of opportunities and constraints shaped by factors entirely outside their control. The generation ship intensifies this condition to an unusual degree, but does not create it from nothing. The counter-argument that the ship's inhabitants would nonetheless have lives worth living within a community capable of meaning, discovery, love, and creation is not obviously wrong, nor is it obviously sufficient. The conversation sits unresolved at the edge of a serious practical problem, waiting for the engineering to be solved enough that the ethics become genuinely urgent, rather than merely speculative. Alternative approaches to the multi-generational problem include induced hibernation, placing the crew in a state of dramatically reduced metabolic activity for the duration of the voyage, awakening them only at arrival, and digital consciousness transfer, in which human minds are encoded into information and transmitted to the destination at the speed of light, then reconstituted in a substrate awaiting them. Both concepts exist, currently entirely in theory and science fiction. Human hibernation, true suspended animation beyond the modest metabolic reductions achievable with current cooling techniques, has not been demonstrated and may not be physiologically possible. Digital consciousness transfer raises questions about personal identity, continuity of self, and the nature of experience that physics and neuroscience cannot currently answer. The technical barriers are genuine and profound, but so once were the barriers to orbit. The history of space exploration is a history of engineering the apparently impossible into the merely very difficult. That history gives no guarantee of success in these cases, but it counsels against certainty of failure. The nearest known exoplanet to our solar system is Proxima Centauri b, a world orbiting within the habitable zone of Proxima Centauri, the red dwarf star 4.24 light-years from Earth. Proxima B's mass is at least 1.07 times that of Earth, placing it within the range of rocky terrestrial planets. Lasix, placing it within the range of rocky terrestrial planets. Whether it could support liquid water on its surface, and whether it has an atmosphere capable of sustaining that water, depends on factors not fully resolved, including the intensity of ultraviolet and X-ray radiation from its host star, which is a flare star prone to energetic outbursts. There may be other planets in the Proxima system not yet detected, and there are other promising candidates within reach of interstellar missions at various distances. TRAPPIST. One system of 7 rocky planets, some in the habitable zone at 39 light-years. Tau Ceti's planetary system at 12 light-years. The destinations, in other words, exist. The question, as always, is the journey. There is something profoundly quieting about placing yourself, in imagination, aboard a generation ship in transit. No longer in the warm interior of a solar system illuminated by a familiar star, but in the cold, dark region between stellar systems, where the sun has dimmed to one bright star among thousands, and the destination star has brightened enough to be noticeable but not yet dominant, and all around the ship, in every direction. The people inside go about their lives, eating what the ship grows, sleeping when the lights dim, caring for each other in the only community available to them, raising children who will do the same. Ahead, a century away, another world waits, unknown, unvisited, not yet anyone's home. Behind, faded now to insignificance in the star field, is the world that sent them. Between those 2 points, which is everything they have ever known, they live. Completely. Fully. Each generation complete in itself. Not merely a vessel for the journey, but the thing the journey is actually made of. Re-entry is perhaps the most physically dramatic phase of any crewed spaceflight, a controlled fall through the upper atmosphere at speeds of more than 27,000 kilometers per hour, during which the kinetic energy of orbital velocity is converted into heat through compression and friction with the air. The plasma sheath that forms around the vehicle during peak heating reaches temperatures of roughly 1,650 degrees Celsius on the leading surfaces, hot enough to vaporize most metals. Thermal protection systems, ablative heat shields that slowly burn away in a controlled manner, carrying heat away from the vehicle's surface, or ceramic tiles that insulate the underlying structure, must withstand this environment for the several minutes during which heating is most intense. The ionized plasma surrounding the spacecraft also blocks radio communication with the ground, creating a communication blackout period of several minutes during which mission controllers on the ground can only wait, watching the telemetry trail go silent, knowing the next contact will confirm either success or something they do not want to name. The deceleration during re-entry, the G-forces acting on the crew as the atmosphere breaks the capsule's descent, is one of the most physically demanding aspects of a return from orbit, particularly for crew members who have spent 6 months in microgravity and whose cardiovascular systems have adapted to the absence of gravitational loading. Peak re-entry deceleration for a typical crewed capsule reaches 3 to 4 times the force of gravity, 3 to 4 G sustained for several minutes. For a body accustomed to zero gravity, this is extraordinary. Blood pools toward the lower body under the acceleration load. Vision can dim at the periphery. The chest feels heavy and breathing becomes effortful. Most returning astronauts manage this with practiced techniques. muscle tensing, rhythmic breathing experience. But the contrast between the weightlessness of orbit and the sudden, intense weight of re-entry is one of the most visceral physical transitions available in human experience. You have been weightless for 6 months. Now you weigh 4 of yourself. It does not last long, but it is not gentle. After landing, whether by parachute descent to the ocean in a splashdown or to the step in a Soyuz touchdown, the moments of first contact with Earth are a complex sensory experience that returning astronauts describe in consistent, striking terms. The smell of the air is the first thing. Real, biological, complex air, carrying the smell of soil and grass or salt water and sea, the countless aromatic planetary biosphere that the recycled, processed air of the station never contains. The weight of the body is next. A returning astronaut lifted from their capsule and placed in a recovery chair cannot stand unassisted. Their legs, months detrained, cannot yet bear their body's weight. The ground crew supports them while the cardiovascular and musculoskeletal systems begin the slow recalibration that will take weeks to complete. And the sky, open above them, infinite in a different direction, and space is infinite, blue in a way that the void never is. After months of looking at Earth from outside, they are back inside it. The rehabilitation process after a long-duration spaceflight takes weeks to months and involves a structured program of physical therapy, cardiovascular reconditioning, and careful medical monitoring. The muscles of the legs and core, most affected by the absence of weight-bearing loading in orbit, must be rebuilt through progressive exercise. Balance and coordination, governed by the vestibular system, which recalibrated to weightlessness over months, and must now recalibrate back to 1G, takes days to weeks to restabilize, during which returning astronauts may feel mildly uncoordinated and need assistance with navigating stairs or uneven terrain. Bone density lost during the mission recovers more slowly than muscle, over months, not weeks, and may not fully recover to pre-flight values in all crew members. Fluid redistribution reverses within days as the cardiovascular system adapts back to the demands of standing upright. The body, given time and the right support, largely recovers. But the process is patient and slow, a mirror image of the adaptation that occurred in the opposite direction at the start of the mission. On February 14, 1990, the Voyager 1 spacecraft, then more than 6 billion kilometers from Earth, beyond the orbit of Neptune, turned its camera back toward the inner solar system at the request of astronomer Carl Sagan. The resulting image, now one of the most famous photographs in human history, showed the Sun and several planets against the darkness of space. Earth appeared as a barely resolvable point of pale blue light, less than a pixel in size, suspended in a beam of scattered sunlight, surrounded by the vast emptiness of interplanetary space. Sagan called it the pale blue dot, and the meditation he wrote about it, about the smallness of our world and everything that has ever happened on it, set against the indifferent scale of the cosmos, remains one of the most eloquent passages in the literature of space exploration. The photograph did not show a civilization. It showed a mote, pale, small, alone, and unexpectedly moving. The history of the human space age is less than a century old. Yuri Gagarin became the first human being to orbit the Earth on April 12, 1961. Not quite 65 years ago, as of this writing, Neil Armstrong and Buzz Aldrin stood on the surface of the Moon on July 20, 1969. Within a single human lifetime before today, the International Space Station has been continuously inhabited since November 2000. The first commercial crewed flights to orbit flew in 2020. The entire span from Sputnik's first orbit to the present day is shorter than the lifespan of many people alive. Right now, we are, in the oldest perspective available, newcomers to space, tentative, recent, and still very much learning. Every human being who has ever traveled beyond Earth's atmosphere could fit into a large lecture hall. Fewer than 700 people have crossed the Kármán line in the entire history of our species. The age of space remains, in the largest possible sense, just beginning. The reasons human beings go to space have always been multiple and not entirely separable. Scientific curiosity, national prestige, the commercial development of orbit, the long-term survival imperative of becoming a multi-planet species, and something harder to name. A drive that has always sent some human beings toward the edges of the known. Not because the known was insufficient, but because the edge was there, and because edges are where discovery happens. Each of these motivations is genuine, and each has shaped the history of the space age in different ways. The scientific results of crewed spaceflight are real. Medical research on microgravity physiology, materials science conducted in the absence of convection, Earth observation from orbit, and astronomical observations above the atmosphere have all produced knowledge with tangible applications. The prestige dynamics of the space race produced an engineering effort of extraordinary speed and ambition. The commercial turn has made access to orbit more frequent and gradually less expensive, and the existential motivation, the species' survival argument, grows more rather than less relevant with time. Astronauts who have spoken most candidly about the experience of returning from space often describe a lengthy period of quiet reintegration, not the triumphant return of the narrative, but a subtler, more private process of re-inhabiting an ordinary life that has been made to feel slightly strange by the contrast of what came before. The grocery store with its 10,000 choices, the traffic, the noise, the endless complexity of a social world built for dense, fast-moving human interaction. All of it remains as it was before the mission, and yet all of it is seen for a while, through the eyes of someone who has recently looked at the whole of it from 400 kilometers away, contained within a window, quiet and small, and entirely blue. Most astronauts find their ground legs within a few weeks. Most re-engage with ordinary life with genuine warmth and energy. But something remains permanently recalibrated. A deep, earned sense of proportion that becomes part of who they are for the rest of their lives. The science of living in space has advanced significantly from the early days of the space age, when the physiological effects of weightlessness were largely unknown and had to be discovered through the lived experience of the first cosmonauts and astronauts. We now know, with considerable precision, how much bone density is lost per month in microgravity, which countermeasures mitigate the loss most effectively, how the vestibular system recalibrates, and at what rate, how fluid redistribution affects intracranial pressure, how radiation exposure accumulates over mission duration, and how sleep is affected by the 16 sunrise day. The body of knowledge built from decades of crewed spaceflight is the most comprehensive record ever assembled of how human physiology responds to an environment fundamentally different from the one in which it evolved, and it is directly applicable to the design of future missions, future habitats, future medical countermeasures, and future spacecraft. Every mission adds to this record. Every astronaut is, in a medical sense, also a research subject, and their willingness to be so is one of the quiet contributions of the human spaceflight program that goes largely unnoticed in scientific literature. The question of whether humanity will become a spacefaring species, genuinely multiplanetary, with self-sustaining communities beyond Earth, or whether the current space age will remain a technological achievement without civilizational transformation, is one that cannot yet be answered. The technical barriers to multiplanetary living are real and significant, as this script has tried to describe with some honesty. The psychological, social, and ethical barriers are equally real and have received less sustained attention. And the question of whether enough people will choose or enough institutions will commit to the generational, resource-intensive, and deeply uncertain effort of actually building human communities beyond Earth is one that depends on variables no one can control in advance. What seems clear is that the desire to go, the pull of the edge, the curiosity that sent Gagarin into orbit and Hubble to Palomar, and every navigator who ever sailed beyond the horizon, is not going away. It is older than the space age. It may be older than civilization. The night sky, seen from a truly dark location, far from the light pollution of cities, under a sky that has not been washed pale by human illumination, is the same sky that has hung over every human civilization that has ever existed. The same stars, the same constellations, the same slow wheel of galactic structure, visible in the Milky Way's arch from horizon to horizon. Every culture that has ever produced a sophisticated astronomical tradition did so by looking at the same sky you can look at tonight. If you are in the right place, with the right darkness around you, and every rocket that has ever climbed toward orbit has been climbing toward that same sky, the one that was always there, that was always vast, that was always waiting for something small and curious and alive to stop looking and start going. The sky is not an obstacle. It never was. It was always the destination. Space travel is the species finally, slowly, beginning to go where it always looked. Light from the sun takes approximately 8 minutes and 20 seconds to reach the Earth. This means that the sunlight warming the air outside your window right now left the sun's surface 8.5 minutes ago, and the fusion reactions that produced it may have occurred tens of thousands of years before that. Since photons generated in the solar core take an extraordinary long time to random walk their way to the surface through the dense, opaque interior. The light of the stars you see tonight left their surfaces years, decades, centuries, or millennia ago. The universe you observe is always an archive, a record composed entirely of light from the past, assembled into an apparent present by the physics of propagation and the biology of precession. Spacefaring civilizations would experience this in a more intimate and operational way, navigating by the positions of stars that are seen where they were years ago, not where they are now. The universe is not just large, it is historical. Looking at it is always simultaneously looking backward in time. The astronauts who have traveled farthest from Earth are the Apollo 13 crew. James Lovell, Jack Swigert, and Fred Haise, who during their aborted lunar mission in April 1970 swung around the far side of the moon on a free return trajectory, reaching a maximum distance of approximately 400,171 kilometers from Earth. They remain the human beings who have traveled the greatest distance from their home planet in the history of the species. They were not supposed to reach that distance. The mission was supposed to land on the moon's surface. An oxygen tank explosion in the service module forced the abandonment of the landing and the improvised use of the lunar module as a lifeboat, and the crew spent 4 days coaxing a crippled spacecraft around the moon and back to Earth with no guarantee of success. They made it. all three came home safely. Of all the distances traveled in the history of human spaceflight, theirs remains the record, set not in triumph, but in survival, which in its own way is the more human achievement. At this moment, somewhere above the Earth, a crew of human beings is orbiting the planet at 28,000 kilometers per hour. They have been there for weeks or months. They are sleeping in tethered bags, or working through a morning schedule, or looking out the cupola window at a weather system, forming over an ocean they know by name. They are drinking recycled water, and eating rehydrated food, and exercising on a treadmill held down by bungees, and they are doing all of this in a sealed metal structure, 400 kilometers above the surface of a planet where every other human being is currently alive. The gap between them and the rest of humanity is 400 kilometers of vacuum. The gap between their experience and anyone else's is not easily measured. They are there right now as you read or listen to this, carrying the ongoing, unbroken thread of human presence in space that has persisted without interruption since the year 2000. They will come home, others will follow. The thread will hold. Every human being who has ever lived was born on Earth. This fact, so obvious it barely registers, is, on a long enough timescale, a temporary condition. The solar system contains enough material, enough energy, and enough potentially habitable environments to sustain human life far beyond in number and diversity anything our home planet alone could support. The universe beyond the solar system contains 2 trillion galaxies, each containing hundreds of billions of stars, most of which host planets. The argument that life, once arisen, has a natural direction towards spreading outward, not inevitably or certainly, but as a real possibility is not obviously wrong. Whether humanity follows that direction is not a question anyone alive today will fully answer. It is a question whose answer will be composed by decisions made over centuries, by people not yet born, in circumstances not yet determined. But the first steps, the rockets, the orbits, the stations, the Mars plans, the sail prototypes, the generation ship thought experiments, are already taken. They are already in the record. They point in a direction, and the direction is outward, always outward, into a dark that is not empty but full, patient beyond all human measure, and waiting. And so we come to rest, here at the edge of what is known and the beginning of what isn't. Somewhere above you, a station passes. Somewhere in the deep interplanetary medium, a probe is sending home the last of its power in a signal so faint that it takes an entire antenna farm to recover it. Somewhere on a drawing board or a simulation screen, an engineer is working through the thermal budget of a habitat that no one will build for decades, if ever, preparing in advance for a problem whose time has not yet come. Space is patient. It does not need us to hurry. It will be there in the morning, and in a century, and in 1 billion years after the last of our descendants has found wherever they are going. It holds no urgency. It makes no demands. It simply continues. Vast, cold, radiant with signals in wavelengths we cannot see, strewn with worlds we have not visited, threaded through with the light of stars that burned and died before the Earth existed. You are very small. You are temporary. You are, in the improbable arithmetic of physics and chemistry and biology, awake, able to know that the universe is large and that you are small within it, and to find that knowledge not crushing but clarifying, not frightening but restful. You have already traveled far enough tonight. The station will pass again in 90 minutes. The stars will hold their positions. The void will continue its patient, ancient business of being there.